Today's lesson is on exponential functions. Take a moment and think about what these two things have in common. That's right. If you said that they'll both be around for hundreds of thousands, if not millions of years, then you're correct. We're also going to learn in this lesson that they both can be modeled by exponential functions. In fact, if you put both of these things together, you get, that's right, a radioactive rat. So listen carefully, young ones, for one day you will be tested on this. Alright, so what are the learning goals today? Today we're going to identify growth and decay functions. We're going to be able to write growth and decay functions. We're going to be able to solve exponential growth and decay problems. And then finally identify the percent rate of change in an exponential expression. So what is an exponential function? Well, an exponential function is a function that has a variable in the exponent. The word exponent is right in the word exponential. So take a look at this function. Here we can see that this function is exponential since the input variable, which I have as x here, is in the exponent. So we would say this function is exponential. However, take a look at the function on the right. Here we can see that the input variable x is acting as a base being raised to a constant power. So this function is not exponential. In fact, this is a polynomial. Alright, exponential functions are used to model situations, right, where something is growing at an increasing rate or when something is falling or decreasing at a decreasing rate. These functions grow or decay by a common ratio. That means that consecutive outputs are multiplied or divided by the same number. This is in contrast to a linear function where consecutive outputs, right, are being added or subtracted with the same number. Right, when something is increasing at an increasing rate, we call this exponential growth. Classic examples of exponential growth include population growth and compound interest. Right, when we say something is falling or decreasing at a decreasing rate, we call this exponential decay. And classic examples of exponential decay include depreciation of a car and radioactive decay. When something is growing at an increasing rate, we've talked about that being called an exponential growth, and that it's increasing by a common ratio, which means to get from one output to the next output, you multiply or divide by the same number, right? Or if something is increasing by the same percentage rate each time, then that's exponential growth. Here is the exponential growth model, where A is the initial amount of something. And then R is what we call the growth rate, and it's always a percent written as a decimal. In this case, I have x as the input variable. In our exponential growth models, that variable is usually time. And then the entire base, the 1 plus r, we call that the growth factor. That's that common ratio that we talked about, what you're multiplying to get from one term to the next. And it's always greater than 1 when you have exponential growth. To illustrate that, we can see that if I take a number that is greater than 1, like say 2, and I raise it to the first power, I get 2. If I take 2, now the same base, and I let increase x, because that's our variable, right? Now I let x be 2, we get 4. If I take 2 and raise it to the third power, we get 8. And I could keep going on, but you see how this is growing. In this case being multiplied by the common ratio of 2. So as long as that base, this growth factor, is greater than 1, you're going to have exponential growth. Exponential growth functions look like what I have on the right. And you can see that they grow slowly at first, but then explode and grow really quickly. So let's do an example writing exponential growth models. First example we're going to do is compound interest. So suppose you deposit $1,500 in an account that pays 2.3% interest compounded every year. That means every year I'm going to take your investment, your 1,500, and I'm going to add 2.3% more to it. And then the year after that, I'll take that new total and calculate and add 2.3% to that. So what is the initial principal, right? The initial principal is always the amount that's invested. Then I want you to think about what the growth rate is going to be and what the growth factor is going to be. And then finally, we're going to use this equation to figure out how much money we have after 2 years if we didn't deposit any more money into the account. And you notice that this is nothing more than the exponential growth model, where I've written P for the principal instead of for A as the initial amount. And our input variable is going to be T for time because we want to know how many years we will have the initial principal being $1,500, right? And the growth rate is, remember, that's the R, and it's always written as a decimal. So we took the 2.3% and we moved the decimal back 2 times, or we divided 2.3% by 100, and that's how we got 0.023, which is 2.3% as a decimal. That is the growth rate. And the growth factor then is when the entire base, which would be 1 added to the 0.023 to get 1.023. So let's figure out how much money we would have after 2 years. To figure out how much money we have after 2 years, I just plug in the appropriate quantities into the equation, where I'm going to go ahead and use the P is our principal, which is the initial amount invested. That's for $1,500. The 1 is part of the equation. The growth rate is 2.3%, or 0.023 as a decimal. And finally, we let T be time in years. So we plug in a 2 for T. So the next step after this would be to add inside the parentheses following the order of operations to get 1.023. And then following the order of operations, I have to square that number. So I took 1.023 and squared it, and then multiplied it by 1,500, and I came up with this amount, $1,569.79. Another classic example, right, is population growth. So let's talk about a population of 20 rabbits being released into a wildlife region. Right, the population is growing at a rate of 60% per year. We want to A, write the exponential growth model, and then B, determine how many rabbits there will be after 5 years. Alright, so I always like to start off with my exponential growth model. So here's our classic basic equation, and remember, I'm trying to find out what A, R, and T should be. Alright, so let's go ahead and A, remember, this is the initial amount of whatever we're talking about, in this case rabbits, and we start out with 20 rabbits. R, they tell us this time, is the growth rate of 60%, which is 0.60 as a decimal. Alright, so then I end up with this exponential growth model of 20 times 1.60 raised to the t. So now I could use this equation to figure out how many rabbits there'll be in any given year that I want. In this case, we want to figure out how many rabbits there'll be after 5 years. So I go ahead and replace t with 5 and then solve the equation using a calculator. And we get that there's about 210 rabbits. Now let's go ahead and take that same problem and let's graph it and make a table. Alright, so recall that here is our equation to model the population of these rabbits. And if the question here was to ask you again, what is the growth rate? What is the percent rate of change you would look at the part after the 1, and that's 0.60, or that's 60%. So you can also get that by looking at the equation. So now the next step to graphing this is to make a table. So quickly I've generated this table, and all I did is go ahead and increment t, letting t go from 0 all the way up to 5 in this case, because we wanted to know how many population after 5 years. Notice that when I plug in a 0 for t, I take 1.60, raise it to the 0 power, and recall that anything raised to the 0 power is 1, not 0. So 1.6 raised to the 0 power would be 1, and then 1 times 20 gives me 20, or the initial amount of rabbits. So a time of 0 corresponds to the initial amount of something. Next, I took turns plugging in 1 for t, then 2 for t, and again using my calculator to generate these values out here. Now, there's another way, right, when you can tell a model is exponential by just looking at a table. So suppose I was just given the table. Now we know that this table does represent an exponential growth model because we generated it using our exponential function. But supposing I didn't have the exponential equation, and I had just had the table, and I was asked, does this represent data that is exponential? Is what I would be looking for is that between consecutive terms I had a common ratio, that I was either multiplying or dividing by the same number. Alright, and the way that I do that is take any two terms, so I took the first term here, and take one and divide it, take one output and divide it by the output that came before. So in this case I'm going to take 32, divide it by 20, and I see that I get 1.6. Yes, 1.6 is our growth factor. So to get from one term to the next term, I should be multiplying by 1.6. So to get from 32 to 51, I should take 32 and multiply it by 1.6 and get 51. And you can go ahead and try that on your own on a calculator and verify that you do get that. In our case, it's going to be a little bit off because I rounded these number of rabbits to the whole number, right? Because it doesn't make sense to have a 0.2 of a rabbit. Just to make sure it's exponential, I'm going to grab a couple of other points on the table and just take 1 and divide it by the output that came before. So in this case, 82 divided by 51, and I got very, very close to 1.6. So I would say that this model is in fact exponential, and we know that it is. Now once that I have the table generated, I'm going to go ahead and pull up a coordinate plane and plot those points. So here you see our initial value at 0. We would plot a point at 20 because the y-axis represents the number of rabbits, and the x-axis in this case is t and represents years. So after 1 year we have 32 rabbits, and then we plot that point. And then finally I plot the other points in the same fashion and then connect them with a smooth curve. If I wanted to know how many rabbits came in the 6th year, I'd have two options, right? I could plug in a 6 where there is t in our equation, or since I know that the 5th year we had 210 rabbits, I could just take that and multiply it by our growth factor, which is 1.6. So in year 6, there's going to be 210 times 1.6 more rabbits. Let's go ahead and write another exponential growth model. This time, we have a population of 5 zombies. Okay? And each zombie infects 4 new people each day. So we're going to answer these questions. 1, we have to figure out what is the initial number of zombies. 2, what is the growth factor? 3, we're going to write that exponential growth equation. And then we're going to figure out how many zombies are going to be in 10 days. All right, so I always start out with my exponential growth model, and I start plugging in the values. So from the problem, we can see that we start out with a population of 5 zombies. That's what A is. So where A is going to be replaced with 5. Now we have to think about what the growth factor is. In our previous problems, remember R is expressed as a percent rate of change as a decimal. Well, here we're not given a percent rate. We're just told that each zombie infects 4 new people each day. Alright, so if one zombie is infecting 4 others, then we would say that they're quadrupling every day. So that in this case, the entire growth factor, the entire base should be 4, because they are multiplying, each zombie multiplies, makes 4 more each day. So like we said, A is going to be 5, and then the growth factor is going to be 4, so I let the R be 3. So finally we come up with the exponential growth model, that the population of zombies after t days is equal to 5 times 4 raised to the t. So now finally answering the last question, how many zombies there will be in 10 days, just requires us to replace the value t with 10 and solve using the order of operations. So we get that 4 raised to the 10th power is this very large number over 1,000,000, and then when we multiply that by 5, we come up that with in 10 days there would be 5,242,880 zombies. And that's a lot of zombies. Alright, so now you try it. And the problem here is we have too many rats. Right? Rats were introduced to the Hawaiian Islands accidentally as they escaped off the ships of explorers like Captain Cook. Right? The rat population can be modeled by the following equation, where we're going to use t to represent time in months. The picture that you're looking at on the right is called a rat king. In fact, these are the remains of a rat king. Right? And a rat king is when the tails of many rats get entangled and knotted together and they can't escape. Alright, so we're going to want to know first, what is the initial number of rats that escape the ships? What is the percent rate of change, or the growth rate of the rats? How many rats will there be after 12 months? And then how many rats will there be after 3 years? Supposing that none die and none get eaten. So I'm going to give you a moment to pause the video and answer those questions using the exponential growth model. Alright, so let's go ahead and tackle these questions. A, what was the initial number of rats that escaped? Well, by looking at our model, we can tell that the A is 30, which represents the initial amount. So just from the equation, this number that's being multiplied out in front, remember that's our initial amount. So in this case, it's just 30 rats. Next, we want to know what is the percent rate of change. What is the percent rate of change? And to get that, I just have to take our number here, that's the base, this 1.29, and subtract 1. Or look at the part that comes after the decimal if there's a 1. So in that case we get 0.92, and 0.92 is 92%. So I would say there's a 92% rate of change. That means each month there's 92% more rats than there were the month before. So now let's figure out how many rats it's going to be after 12 months. Okay, so in order to do that, I take our equation and replace t with 12. Then using the order of operations on our calculator, we see that there's going to be roughly 75,290 rats. So now how many rats are there going to be after 3 years? Be careful on this one. The common mistake is people to say, I'm going to plug in a 3 where the t is. But notice that this is years and t represents months. So if I'm going to replace t with the correct number, I need to figure out how many months is in 3 years. And since there's 12 months in 1 year, 3 times 12 is 36. So I go ahead and let t be 36 if I want to find out how many rats there's going to be in 3 years. Then I solve this equation using the calculator, and I get this ridiculously large number of over 474 billion rats. In real life, they die off, and predators eat them, and the population of the island can't support them because they don't have enough food, so you don't get up to, thank God, 474 billion rats running around. Now let's talk about exponential decay. Okay, when something is decreasing at a decreasing rate, we call this exponential decay. Alright, in fact, the output, which we call f of x, is decreasing by a common ratio for each consecutive input. And usually that input is time. If something decreases by the same percent each time period, then that's called exponential decay. Alright, and the equation for exponential decay is modeled this way. If you'll recall, it is almost the same as exponential growth, except for there is a minus in between the 1 and the rate. So this time we'll be taking 1 and then subtracting away that percent growth. And again, a, of course, is the initial amount of something. So that number being multiplied out in front represents the initial amount of whatever it is we're talking about. R is the decay rate, is written as a decimal. X is the input variable, and usually that represents time when we're talking about something happening over time. And then the entire quantity, 1 minus R, represents the decay factor, or it's the percent remaining. So for example, if I had something that was decreasing by 10% each year, the decay factor would be 1 minus 0.10, or leave you with 0.90, which would indicate that you have 90% of what you had before. So you took whatever you had and you kept 90% of it, would be the interpretation. Exponential decay has graphs that look like what we have here on the right, where something starts out, whatever number it starts out as is the A, and then decreases rapidly at first, but then more slowly as time goes on till it approaches some constant value. Alright, so let's look at a classic example of depreciation. Suppose you buy a new car and it depreciates according to the model below. I want to know, 1, what was the original price of that car? 2, what is the percent rate of change? And 3, what will the car be worth after the first year? And then what will the car be worth after the second year? Alright, so the original price of the car can be found by just looking at the equation and realizing that the value in front, this $22,500, represents our initial investment into the car, what we bought it for when it was brand new. Now we want to know what the percent rate of change is. Alright, so when you're asked these on your questions and your lessons, and it says what is the percent rate of change, when you're looking at growth, you're looking at doing 1 minus the growth factor, and we're going to do the same thing whether it's decay or growth. So in this case, I take 1 and I subtract the 0.93 here, and I get 0.07, which is 7% as a decimal. So the car is depreciating by 7% each year. So that is what we call the percent rate of change, because it's going down 7% each year. Another way to interpret it when you're looking at the model is it's going down 7% each year, so it's retaining 93% of its original value, right, from the time period before. So it's retaining 93%, that means it went down 7%. And then finally, what's the car going to be worth after the first year, after the second year? Since we have the model, that's easy, right? We just take turns replacing t with the appropriate value. So after the first year, we let t be 1. We use our calculator and we get that the car is going to be worth $20,925. So it's depreciated almost $2,000. For the second year, we take our exponential decay model, go ahead and let the t be 2 for 2 years. Solve this equation. Remember, we have to raise the base to the power before we multiply, following the order of operations. And we get that the car will be worth $19,460.25 after 2 years. In this case, since we're dealing with money, they always pretty much expect you to round to the nearest penny, right? So round to the last cent, 2 places after the decimal. Another classic example when we're dealing with exponential decay models is what they call radioactive decay. So take a look at this example, half-lives matter. Right? Iodine-131 is a radioactive isotope used in medicine. Its half-life or decay rate is 50% in 8 days. That means that after 8 days, 50% of the original amount will remain. And then if 8 days after that, that will be cut in half, and so on and so on. Now, if a patient's given 25 milligrams of iodine-131, how much would be left after 32 days, or 4 half-lives? Because remember, a half-life in this case is 8 days, so 32 divided by 4 gives us that 8 days. So 32 days would represent 4 half-lives. We need to identify what the A, the T, and the R is. Go ahead and tell me what the decay factor is, and write down the equation you would use to solve it. Alright, so here's our problem setup. I always want to start with thinking about my exponential growth model before I start plugging in my values, so I know I need to know what the initial amount is. Well, it says here that the patient is given 25 milligrams of iodine-134, so our initial amount then is 25. The time period here is 4, because we want to know how much would be left after 4 half-lives, and we're letting t represent the number of half-lives in this case. How about r, which is the decay rate? Well, it tells us here that the decay rate is in fact 50%, so we don't have to do anything to get it. 50% written as a decimal is 0.5. Remember, you just divide by 100 or you move the decimal back 2 times. And the decay factor is the entire quantity 1 minus 0.5, which in this case gives us back to 0.5. So something is decreasing by 50%, it's also retaining 50% of its original value. So here's our exponential decay model. I'm going to plug in the values into the equation. So A was 25, and R was 0.5, and T was 4 for our 4 half-lives. Then I just solve this using order of operations. And we get that after 32 days, or 4 half-lives, this patient's going to still have about 1.56 milligrams of iodine-131 in his or her body. So we started out with 25 milligrams, and it decayed until after 32 days there's 1.56 remaining. Now, if you looked at the graph of this, is what you would see is that in the beginning, it went down quite a bit. It went maybe after the first half-life, went from 25 milligrams, right, to 12 milligrams, like decreased by 12. But then after that, it only went down to 6, and then to 3. So see, it's being cut in half each half-life. All right, now you try. Here we're going to do a problem writing exponential decay models. Problem is, all we need is a little plutonium. Those of you who have watched the movie Back to the Future will know the reference. Alright, so here we have Doc Brown. He uses 5 kilograms of plutonium-239 to fuel his flux capacitor so that he can achieve time travel after hitting 88 miles per hour. Now, plutonium-239 has a half-life of 24,100 years. That's why this stuff is so dangerous to store for long periods of time. You need a permanent solution. Alright, now that means that 50% of the original amount of plutonium-239 will remain after 24,000 years, whatever original amount that is you started with. So I'm going to have you write an equation that models that situation, and go ahead and let t represent the number of half-lives. Right? Then I want you to figure out what the percent rate of change is. And then finally, figure out how much plutonium will remain after 241 years, which is 0.01 half-lives. And round your answer to 2 decimal places. So go ahead and pause the video and take a moment to try to complete those parts of the problem. Alright, so I'm going to start out with my exponential decay model. And we see that the initial amount is 5 kilograms. So where there's A, I plugged in a 5. And then this is decreasing by 50%. So the decay rate is 0.50, and 1 minus 0.50 gives us 0.50 again. And then we go ahead and raise that to t, which t is representing our number of half-lives. So writing the exponential model when you're given the appropriate information is easy. Now we got to talk about what is the percent rate of change. Alright, and to get that, all I would do is take 1 minus this value in here, and in this case we come back to 50%. In fact, it tells us, right, that a half-life means 50% the original amount. The percent rate of change is 50%. So finally we're going to use our model to figure out how much plutonium will remain after 241 years. Remember, since we let t represent the number of half-lives, we're not going to let t be 241 because t does not represent years here. It represents the number of half-lives. So in this case, 241 years is only 0.01 half-lives because the half-life of plutonium is so large at 24,100 years. Right, that 100th of that would be 241 years. So we're going to go ahead and let t be 0.01 in this case. Alright, so then I go ahead and I solve this equation. And I take 0.5 and raise it to the 0.01, multiply it by 5, and you can still see that after 241 years there'd be 4.97 kilograms, almost all of it still remaining. We only lost 0.03 of a kilogram. Alright, so let's give a quick summary of exponential growth and exponential decay. Here are the models for exponential growth and exponential decay. If you're ever asked to identify which one of these models represents growth or decay when you're looking at an exponential function, all you have to do is look at that base, what's being raised to the power, and if that number is larger than 1, it's exponential growth. If that number is a decimal or a fraction, a number that's between 0 and 1, then you get decay. The graph of an exponential growth model looks like the one on the right, where the y-intercept always happens at that initial value. So 0a is our y-intercept. Same with the exponential decay model. So the y-intercept happens at 0, whatever the initial amount was. So when you're looking at a graph, that's what exponential growth looks like, and this is what exponential decay looks like as it falls and decreases to the right. Then we talked about what each of those in the equation represent, each of those values in the equation. All right, so R is the growth rate, and it's a percent written as a decimal. X in this case is usually represents time, but it's our input variable, so you see that it's the exponent that's changing as we let it get larger and larger. And then finally, the quantity 1 plus R is either the growth factor, a number greater than 1 if it's growing, right? It has to be. If we add a positive number to 1, it's going to be bigger than 1, and we're going to get growth. And then the decay factor is 1 minus some percent, written as a decimal, which should end up being a decimal, a number between 0 and 1 again. And since that number would be less than 1, when we raise that to a power, it gets smaller. So that concludes today's lesson.